So this segment is about section 2.1 in the app book. Sort of an intro to logical thinking, logical form, I think is what they call it. She calls it. So it starts off by discussing what makes an argument. And you have to recognize that in math and logic and even philosophy, or really intellectual life in general, arguments don't necessarily imply that people are angry with one another and there's threats of violence or anything like that. Arguments are just about convincing somebody of the truth of some statement that you think is true. So arguments in this sense are very what's the word, bloodless. There's no anger involved. There's no discord. Arguments are just about, here's the facts and here's the deductions we can make from those facts. Let me point you to a funny, not hugely funny, but it was certainly hilarious at its time, a video that you might want to look at. I'll try to put a link to this in the description on YouTube. It's a Monty Python thing called The Argument Clinic. Monty Python was this group of British comedians that got together and formed, I think it was like 6 or 7 of them, a troupe that did comedy back in like the 60s. And some of them are still active in making movies and acting and stuff to this day. One of the prominent members was a guy named John Cleese, who I think occasionally he might now be too old to be getting into any new movies, but anyway. John Cleese, Michael Palin, Eric Idle was another one. Anyway, they're pretty famous in the day. The Argument Clinic has this weird little moment in it, so it's about a guy who is visiting a store where they sell sort of experiential things. At one point, he never mind. I won't spoil the video for you, but if you want to watch it, it's fun. He goes in to get an argument because he thinks it would be fun to have a nice intellectual debate with somebody. So he pays money to have an argument with another guy, and then hilarity ensues. At one point in this discussion, though, they literally say the precise philosophical or scientific definition of what an argument is. So he says, an argument is a connected series of propositions designed to establish a definite conclusion. And I was like, wow, that's right out of the book. He said it exactly. So I think these Monty Python characters actually, while they're working as comedians, they must have had a good liberal arts education where they learned stuff like that. Anyway, let me give you a visual for what an argument looks like. You're going to start off with what are known as hypotheses or premises. There'll be a bunch of them. I'm not going to say in advance how many there are, but press in the middle. There might be 1 premise, there might be 3, there might be 7, but there's usually a small number of premises. Let's just go up to premise number K. Those initial statements are what are called hypotheses. And the etymology of this word is sort of interesting. Hypo means under. Like a hypodermic is something they stick under your skin. Hypo, and then thesis means a concept. In fact, the final thing that we're going to get to after we do this argument is going to be a thesis, a conclusion. So these are the things that lie under the thesis. I think that's kind of cool. Anyway, after the premises, after the things that you get to assume for the sake of the argument, you'll have deductions. And there'll be a bunch of those as well. There'll be deduction number 1 and ... down to deduction number n, say. And that last deduction is called the conclusion. So you probably have heard the word deduction before. What's the big idea? It's that the truth of any one of these deductions follows necessarily from the truth of the ones above it. Let me say that here on the side. The truth of each deduction well, I guess I'll say the same exact word, follows necessarily from the truth of earlier deductions and the premises. Now, we are not going to get too much into how we know that something necessarily follows from the previous stuff, but there are some standard ways of doing this, some particular kind of mini arguments that say, oh, if you have these two premises, you can get this deduction. Or if you have, I don't know, some subset of these things, it'll get you this. As long as the junk above you will guarantee the truth of the one you're at, that's a valid deduction. So before we make too much more discussion of this arguments, we're going to be coming back to that because it's kind of a big deal. Most of the I think at some level the part of this course that troubles students the most is when we do mathematical proofs. Mathematical proofs are nothing but arguments like this, where you're supposed to have a logical connection from earlier statements to later ones. So we will definitely be spending more time on this subject. But before getting into that, at least to finish out today, we need to sort of just get a grounding in how logic works. There's an undefined notion. There's actually a couple of them. They're the words true and false and sentence. And these are weird in the sense that it's almost impossible to come up with a way to say what they mean. What do you mean by true? It's hard to say what true is without using the word true in the process, which that's no good. Similar for false. Although maybe if you said we're able to say what true is, false would just be its opposite. So I guess having the two of these be opposite numbers would be part of the issue. You could define one and then the other would be the negation of that one. Also, sentence is surprisingly hard to define. You can say things, well, it's not awful, but it's a little bit rough to figure out what I mean by a sentence, but we're gonna just sweep all of this under the rug because these are things that, despite them being hard to define, we know what they mean. You know what a true thing is, one that doesn't lead you astray, and a false thing is a lie, and a sentence is, well, I'm making a sentence right now. So a syntactically correct arrangement of words, I suppose. There's a weirdness, though, about sentences that you might not suspect. There are some sentences that are not false, but they're not true either. There are sentences that you can't figure out what they are. One of my favorites is the smallest natural number that can't be described with fewer than 11 words. I think I counted right, because that was 11 words and I just described it. Anyway, the main point of talking about sentences is that we're going to ditch them. We don't want to have that kind of ambiguity around if we're doing logic. So here's a definition for you. A statement is a sentence that is either true or false. and not both, and not neither either. Meaning it's got a definite truth value. You might not know what it is. It might not even be possible to figure out what it is, but you know that it has a definite truth value one way or the other. That's a weird situation, but it's actually how it works. One reason a sentence might not be a statement, for instance, is sentences that are ambiguous. So if we're to have a statement, we cannot have ambiguity. For example, let me say, John is a football player. Sounds like a sentence, and if I know who John is, I'm all set. I could tell you yes or no whether he is or isn't a football player. But as it stands, we don't really know who John is. I might be thinking about John who likes soccer, and so, well, of course, in Europe he'd be called a football player. So, whoops. Anyway, if I'm thinking about John who's a computer scientist and doesn't play sports at all, then that's a false sentence. And if I'm thinking about John, like, I don't know, I can't think of a single football player named John right now because I'm on the spot, but you get the idea. If you have this ambiguity where you list a person but you don't specify them well, I mean, sometimes you have sentences that don't have the name of a person in them at all. What if I just said he is a football player? That sentence stinks because who knows who the he is referring to. So we want to avoid that kind of ambiguity. Watch out for that issue. But that's not the only reason that you can have sentences that fail to be one thing or the other in terms of true or false. Anyway, we are going to use letters to indicate entire statements. This is math for you. They abbreviate everything. That such a thing is called a predicate variable, because another name for statement is predicates. So we're going to use a letter, and for some reason people often use P, Q, and R, lowercase letters. But a predicate variable is a letter that stands for an entire statement. Why would I want a thing like that? Well, what the real point of this is going to be is we want to get at the logical form of arguments. And the form is the same if they have the same kind of connectors between things. There's an example in the text in the second page of this section that you should go through. It turns out when you analyze two apparently different arguments, they actually have the same shape, as it were. And you analyze that shape by figuring them out in terms of predicate variables. And you notice, well, both of them have, a variable ANDed with another variable. So they've got the same shape in that sense. The details of an argument are what the predicate variable actually stands for, what statement is involved, but kind of the overall form of the argument is just how do you connect the predicate variables together. So let's be a bit more concrete and give you an example of that sort of thing. I'll leave the definition of predicate variable right there. But an example that I always like to do is P is equal, it's raining. And Q is equal to the sun is shining. And the reason I'm giving you this particular pair of things is because you can take a pair of predicate variables like this and hook them together into a longer sentence anyway. One of the connectors that we use is the word AND. So if you say P and Q, Well, what does that mean? It's raining and the sun is shining. And I suppose some people would be surprised by that. An interesting language point here. If you've got an and connection like this and you find it surprising, like it's raining and the sun is shining, usually those don't go together, all you do is change the word and into but. It's raining, but the sun is shining. That's how you say it in English. And that points up something kind of interesting. But just means the exact same thing as and. Don't think people don't think about that very often. But yeah, but and are the same idea. The only difference is in sort of the emotional state of the person who's making the proclamation here. But means they're surprised or confused by it. And means it seems natural to them. But that's just their state of mind. But and have the exact same denotation. The connotation is slightly different. Okay, so, but actually we're not going to use either the word and or the word but. There's other connectors you could put in there, like or and stuff like that. But what I want you to do is learn a shorthand, which is this. Let's say this. These are connectors that we'll use. There's a thing that looks like the capital letter A, but without the line in it. It's an upward pointing less than sign, I guess. And that is, its name is wedge, but yeah, wedge. It stands for the connector and or but. And it's got a fancier name, if you like. In logic, they talk about this as being a conjunction. Conjunction in English language usage, particularly in the people who study the language as a topic, a conjunction is any of these sort of connector words that hook up phrases together. And, or, but, nevertheless, there's tons of these little short, well, nevertheless isn't short, but many of them tend to be short. They're all known as conjunctions, but in math and logic, conjunctions are particularly the ones that mean and we have a different word for the or connection. If you have an or connection between two letters, first of all, it's drawn with the direction of that symbol going the other way, and it's known as a disjunction. There actually is one more symbolic thing that I want to introduce here. This is not a connector so much, it's a modifier. It's what's called a unary operation. And in the text, they write it this way. It looks like a tilde. That stands for the word not, and that's called a negation. A formal way to describe it. I also will sometimes slip up and use another symbol for this. So if you see me write a minus sign that's got kind of a hook on the end of it like that, that's just me slipping up and not using the book's notation. Often in logic circles, this is the preferred symbol for logical negation. I want to say a little something about order of operations. You remember the PEMDAS rule for how you deal with stuff in algebra, parentheses, exponents, multiplication and division, adding and subtracting. The PEMDAS rule probably should be written like this, because adding and subtracting are at the same level of precedence. Multiplying and dividing are at the same level. There's no preference. You do multiplying first and then do division. So when you have just an ambiguity because of those things, you just work left to right. That's the rule. With adding and subtracting, just work left to right. And if you really want a particular thing to be done first, you have to use parentheses. You have to go to the head of this PEMDAS rule. So for these things, the and the or, they're like that. There's no preference between them. So and or are at the same level of precedence. not sign binds closer than the and or. So that is, it's a higher precedence. Let me show you what I mean by that with a quick example. Suppose we have predicate variables P and Q, and I do P and Q with a not right there. So does that mean that I'm taking the negation of P and then anding that with Q? Or does it mean that I want to take the negation of what you get if you and P and Q? And because the not has a higher precedence, we do the not first, and then we and. So it's this one, not this one. If you wanted this one, you have to do it with parentheses. So in logic, parentheses comes first, then negation, then and or. The negation works similarly to the minus sign in ordinary algebra, because a minus sign in ordinary algebra is multiplying by a negative. So yeah, but it still actually loses to exponentiation. Anyway, I don't know for that order of operations. Truth tables. Oh yeah, good. To say precisely what these things mean, what the connections between logical predicates mean, we usually just list out every single freaking possibility. Let me show you what I mean by that. If you have two logical sentences, two statements rather, P and Q, what are all the possible combinations of true and false that they could have? Well, they could both be true. This one could be true and this one could be false. The first one could be false and the second one could be true. And there's one more where they're both false. Okay. Is that it? Is that all the possible combinations? Well, the top half of this table, P is true and Q does both options. The bottom half, it's false and Q does both options. And there's no other possibilities for P. It's either true or it's false. And within those subcategories, Q is either true or false. So we've got it all. This is actually the same number of things as how the outcomes of flipping two coins can work. Okay, so I might make a sort of a philosophical point right now. You might view the rows of this table that I've created as alternate realities, different universes, right? You have, today it's raining and it's sunny here in New Haven. Well, actually, it's dark right now, so that's silly. But you know, on a particular moment in time or in a particular alternate reality, both P and Q could be true. But on some different part of the multiverse, we could have them both be false, and any of these other combinations too. So I like to think about each of these things as being a different potential world, which we're kind of analyzing them all at once. All right, let's say what P and Q does then. We'll make a new column for it. It's simple. P and Q is true precisely when both P and Q are true. So in this first alternate reality, P and Q would be a true sentence. And everywhere else, it's false. In fact, as soon as you see one side of the two inputs false, it's false. And it's really false when both of them are false. I'm a little worried that I'm going to slip up and use this alternate convention that I often do. So I'll just tell you about this now. In case I mess up and start doing this, you won't be surprised. It's just that if you're a sloppy writer, and when I'm at the board I try to be careful, but like in handwriting I'm pretty bad. T's and F's are quite easy to mix up. So I often like to, rather than writing F's, I write the Greek letter phi. Phi is the Greek letter for F. If you know Cyrillic, that's the sound for F. And that thing looks a lot different from this thing. So if you see me starting to write phi's where there used to be f's, that's what's going on. It's an ingrained habit that I have because I so easily confuse f's and t's. Okay, so we just wrote a truth table for the conjunction. I'm just going to cheat and use the eraser to write a truth table for the disjunction, because the setup here, the P and the Q, is going to be the same. I'll just change that connector in between those guys. We still are dealing with these 4 different possible worlds that we could be in, where P and Q independently have true or false as their values, and you get these 4 combinations. So how do you think about the truth value of an or sentence, a disjunction? It's often the case that people think of or as representing alternatives. You're either with us or you're against us, right? There's one thing or the other. So this or in logic is not meant to be that extreme. It's not one thing or the other. It's one thing or the other, or maybe both. It's what's known as the inclusive sense of or. So that symbol right there is inclusive. An or sentence is true if either side of it is true. And the only place where an or sentence is false is going to be down here at the bottom. We'll have an F down there. Everywhere else it's true. So that actually leads to a good way to approach truth tables. When you have or sentences, look for the one position where they're false. I'll show you an example of this in a sec. But let's make the similar point. A similar point about and sentences. If you have a sentence that has an and in it, what you should do is look for the one place where it's true. So an or sentence will be false in one row of a truth table, an and sentence will be true in one row of a table. Let me illustrate what I'm talking about there in a couple of examples here. So we're going to change this truth table a 3rd time now. Maybe that's a 2nd time. I want to have us figure out the truth value of this combination, not P, ORed with not Q. Now that's an or sentence overall. It's got some knots in it, but that's fine. So I'm going to look for the one place where it is false. When is an or sentence false? It's when the jump on either side of it is both of them are false. And where is that going to happen? Well, when P is true and Q is true, not P and not Q will be false. So it's in this top row. That is, I know this is the one spot where it's false. And so I'm kind of done because I know everything else will be true. Get that? Those are quick. False in the top row, true everywhere else. Let me give you a 4th example of a truth table. Again, we'll use the same setup, and I'm cheating a little bit in that I'm not redrawing all this. I feel a little bit bad about that, but it's probably not worth your time to watch me redrawing the truth table over and over again. Let me just point out the pattern that you see in there. You see how it goes true, false, true, false? There's like a top block of the table where Q goes true and false, and a bottom half where it goes true and false. And then in the top half of the table, P is true all the time, and in the bottom half, it's false all the time. So it's TF, TF, TT, FF. If you had to get 3 predicate variables, you can extend that pattern, which we will come to in a sec, but let's leave it alone for now. All right, one more sentence that we can work out what its truth table would look like. Let's change the whole thing, sorry. How about we do not P ORed with Q? Wait a minute. I just did an OR. Let's do an AND now. Yeah. Not P ANDed with Q. Well, that's an AND sentence, or in this category, we want to figure out the one row where it is true. Yeah? And an AND is true only if both sides of it are true. So we want Q to be true. That means we're in one of these two rows, either the first or the third row. And we want not P to be true, which means we want P to be false. Okay? Because the negation turns this F into a T, and then, so it's this position. That's where it's true. And then you just fill out everything else with F's. You see how that makes life easier? If you concentrate on the one spot that's got to be in a certain way, then everything else is the other way. One more time, let me say it this way. Conjunctions have a single T. Disjunctions have a single F in their truth tables. There is a topic that we want to introduce next, which doesn't actually necessarily have to do with truth tables, but this is probably, for my money, it's the best way to think about it. And the topic is known as logical equivalence. Some logical things are just the same in terms of what's their logical content. When I use a symbol for this, there's actually two choices to make. One of the symbols people use for logical equivalence is a equal sign with a tilde on top of it. Adding tildes to things is popular apparently in logic. That looks a little weird, doesn't it? Okay, that's better. So that's one thing. Or another symbol that you will sometimes see is a kind of a double-headed, thicked up arrow. So that's symbolic ways to talk about logical equivalence. But what does it mean? Well, two statements, two of these compoundings that we've been doing of logical predicate variables, what do we call compound sentences? I should say compound statements. They're logically equivalent, which I'm going to write LE because that's too long to write. Two compound statements are logically equivalent if in a truth table you see the exact same pattern of trues and falses. That is, their columns in a truth table are identical. Now, that's kind of a bigger deal than it sounds like. If you go to my interpretation of the rows of a truth table as representing kind of alternate realities, because what that's saying is they are equal in every reality. They're sort of things that work across the multiverse, which is kind of powerful then. That sounds like a bigger deal than just saying their truth tables have identical columns in it. Let me give you an example of some statements that are logically equivalent. Actually, maybe first I'll give you an example of some statements that are not logically equivalent, but you feel like they should be. So here's a non-equivalence. If you have the negation of an and sentence, P and Q. Sorry, be careful with my parentheses. Doesn't it look like this should distribute? I think it does, but it's not true. So I'm going to write the equivalent sign, but put a slash through it. The negation of P and Q is not the negation of P ANDed with the negation of Q. So how do we know? Well, you make a truth table, and you can see that these things do not have identical columns, and so you're done. Let me run this truth table for you. Finally, have to rewrite the setup another time. I'm going to want to fit a column for not P and Q, and then a column for not P and not Q. And remember, this setup has a pattern in the second variable where it just alternates true, false, and the first variable alternates but in groups of two trues and then two falses. Let's look at the end one first, because that'll be a little bit easier mentally. It's an and statement. That's the kind that's true in one position. If we can locate that one position, then we get the rest of it for free. And that's not hard because of the nots, or both of them. That and will only come true if the things on either side are true, which means we actually need P and Q to be false because they're getting negated. So if you got two F's in P and Q, not P and not Q will be two T's. That'll get us a T down here. And that means everybody else, the other positions in that column, are falses. Now, this is also an and sentence, and that one is kind of easy because it's the straight up regular and sentence, P and Q. You know that it's true here and false here, here, and here. And why am I writing those symbols tiny like that? Because they don't include the full thing. It's the negation of P and Q. So I was just putting that on there as like scrap work or something. But when you negate them, it's all good. So true becomes false, and then the falses become trues. And then, good form dictates that you erase this stuff because you didn't really need it, but there you go. Now, are these in fact the same? They're both false in the first row, but here's a world, or a reality where they differ. And here's another one where they differ. There's two places where they agree, but there's other places where they disagree. We need them to have the exact same values right on down the line through the rows of a truth table, and they don't. So those guys are not equivalent. Well, what actually does work, what is an equivalence for the negation of P and Q? So let's see if I can just make some changes to fix this up. There's a thing called De Morgan's law. Maybe people have run into it. Augustus De Morgan is this rather famous, I think he was Irish, maybe Scottish. I don't really remember now. But De Morgan was one of the first people to really look into logic in a thorough way, and he realized that if you negate an and, you get an or with the pieces negated. So that is, this is the correct thing to do. And it's a little bit, I think it's a little bit like, remember when you have an inequality and you multiply it by a minus sign? Or if you multiply an inequality by any negative number, you not only negate the pieces that are in there, but you also have to turn the inequality around. It has a little of that feel. We bring the not into P and into Q, sort of distributing it, but there's a price to pay. We have to turn the and into an or. All right, so having said that, this should have been an or should now be an or. Let's verify this equivalence. Let's see that that truly does work. It's an or sentence. For or sentences, we concentrate on where they're false. And they're false if the jump on both sides is false. And because of these knots, that means we want both P and Q to be true. When P and Q are both true, not P and not Q are false. And so the or is false here. And then we get true, true, true. Because those just are everything else. And look at that. False, true, true, true. They agree in both conditions. What I usually do, because after the fact you have to convince the professor that you've actually noticed the right thing, you do something like this. Point at the two things and say identical. Or maybe even identical columns. But that actually is an argument. That's a proof. You've looked at every possible combination of trues and falses for the inputs, and in every one of those scenarios, these two things that look different give you the same pragmatic results. So this equivalence may be thought of as sort of a pragmatic approach to things. They're equivalent if they give you the same true-false values in every possible scenario. Okay, there's one more really easy topic, but one more topic that I need to add before we'll end this by going to a screencast, and I'll show you a table that's in the textbook. Where's that table? Page 49, but I'll show the scan of it when we get to the screencast thing. Anyway, there's one more topic before we go that route, is things that act like 0 and 1. Identity operators for identity. We want to get the identity operators for and or. But I'll remind you of what that means. To be an identity means that like the number 1 times anything at all just gives you that anything at all. So the identity of x is unchanged if you multiply it by 1. Or if I have y and I add 0 to it, well, that's just y. The identity of y unchanged by the addition of 0. So when you have this kind of a number that behaves in this way, you say 1 is the identity for that operation. What would I say here? 1 is the multiplicative identity. That's a hard thing to write out. I had to use a hyphen and break the line in it. Let me just say this one. 0 is the additive identity. 0 is the number that if you add it to something else, it leaves it unchanged. So what could you possibly AND with a P and get P? Well, what you need here in that position is a statement that's just always true. You see, if it's true, then when P is true, of course, you'll get true. And when P is false, you'll get, when P is false, the AND will be false. So, but that means that both sides of this have the same possibilities for all possible values for P. So there's a name for that, a sentence that has that property that's always true, and it's a lowercase t. T is known as a tautology. And it's just got this property that it's trivially true. It's always true. So there are actual examples of sentences that work that way, that they're just no matter what, they're true. You might think, I mean, we could just define T to mean something that's always true. It's like saying this is always going to supply 5 volts of juice, so on a logic board it'll always count as true. But you can actually make up compound sentences that always are true. For instance, what if you took a statement and you just ORed it with its own negation? Think about that. If this side is true, that side will be false, but the OR will be true, and vice versa. If this one's false, that side will be true, so the OR will be true. So taking a sentence and ORing it with its own negation gets you a sentence like this, a tautology. That's another logical equivalence, that little t is equivalent to P or not P. But this is kind of the cool one, or well, I think of it as the cool one, that tautology acts like an identity for the AND operator. There's another one of these. You might not guess what the letter is, but I bet you can guess what it does. If we need a symbol for something that's always true, shouldn't we also have a symbol for something that's always false? And we do. It's a little c, and that stands for a contradiction. But yeah, that's a sentence that is always false. Can you think about doing something similar to this to make us a thing that's equivalent to a contradiction? You can do exactly the same thing, just stick an and in between those. Look at a statement and it with its negation. This is going to be necessarily false in all situations because the things on either side have opposite truth values. To make it ever be true, we'd have to have these both have the same truth value, but that'll never happen because they're negations of one another. Yeah. So tautology and contradiction are kind of fun. Some of the more interesting properties of logic happen by reference to those. All right, so I'm going to move to a screencast and I'll show you this table on page 49. All right, so here's this table that I was referring to. You'll notice it's fairly dense, but I think you'll find that most of the entries in this table are not a problem. You understand them pretty quickly, and in fact, they seem fairly natural. I want to mention one thing which I find distressing. This symbol that is used for logical equivalence is not the one I just told you about, an equals with a wiggly top bar. They've got a triple equal sign, and that's actually used for a different idea. So I'm sort of surprised that they've reused it here. That's used for equivalence in modular arithmetic. I don't like that. I guess we'll live with it, but it's hurting me a little bit. Anyway, that's just notation. We can adapt to different uses of notation. For instance, I think many of you guys will be doing, guys and gals, I shouldn't be sexist, sorry. You will be doing some circuit analysis type stuff, in which case the and symbol will become multiplication and the or symbol, wherever it is, will become adding. That's the shorthand that people use in circuit analysis. This is the mathematical notation. I prefer it. I think multiplying versus adding actually makes it easy to make a particular mistake because you're used to the way multiplying and adding interoperate. Multiplication distributes over addition. What usually doesn't work is that addition distributes over multiplication, but it does when it's and or, and we'll get to that. So I like there being different symbols that really tell me this is not multiplying and dividing, it's something new. All right, so what's in this table? I'll just peek up over the top of it here. We'll look at it. The first one is the commutative law. There's two of them, one for and one for or, and this just means that you can switch the order. P and Q, Q and P, that's the same thing. The associative law comes next. I keep trying to highlight this, that it's a scan, so it's a picture, not text. Anyway, what is the associative law ordinarily? It just means you can put the parentheses in any way you want. So notice that in this expression I'm pointing at, P and Q and R, they're all and connectors. So you can do it as P and Q ANDed with R, or you can do it as P ANDed with Q and R. I'm trying to pause to give you the sense that, but that's the parentheses can go any way you like if every operator is the same. And same here, we've just got the same expression really, except all the ands are ors. You can or P and Q first, and then or that with R, or you can do it in the other possible order where it's P ored with Q or R. Now, if you combine these first two, it means that parenthesization and order can be mixed around any way you like, so long as all the operations are the same. If you have nothing but ors, you can change the order, you can change the time order, which is what parentheses do, and there's, I don't know how many different ways we could fully parenthesize and fully order those symbols, but there's a lot. So at least, 12. A good quiz question, wouldn't it? Anyway, distributive law. Now this is where the logic things behave differently than multiplying and dividing. When you distribute, I'm going to do a little quick writing on the side here, because I want you to see what distributing with regular numbers looks like first. If you do the distributive law, for instance, 3 times 2 plus 1. That's really 3 times 3 would be 9, right? The distributive law says that you take, there's an implied multiplication right there. So 3 times the quantity 2 plus 1. You take both the 3 and the plus sign. Oh, darn, I just said plus. That is not a plus, it's a times. 3 and its times symbol, and you insert it into the junk that's in parentheses in two different places. Once in front of the 2 and once in front of the 1. So you get 3 times 2 plus 3 times 1. And that's 6 and 3, that's 9 as well. And that's how distribution works. You take the item plus the operation and you pop it into both places inside the parentheses. That actually works with powers too. Like if you have x times y raised to the second power is 2, and the fact that it's an exponent come inside and you end up getting x squared times y squared. And you'll notice that once you've distributed that 3 inside the parentheses, or once you've distributed this power of 2 inside the parentheses, there's really no longer any need for the parentheses. They only were there necessary because there was something on the outside of them. Once that something is moved to the inside, you can stop writing them. Okay, so that's distribution ordinarily. How does that look in this setting? Well, in the left side, we have an and distributing over an or. And you notice how it says P anded with Q or R? Both of these next two things have P and up front. P and Q, or with P and R. And it's very similar, but with the roles of or and and switched here. So this is like adding, distributing over multiplying, which doesn't work in regular algebra, but is perfectly fine in Boolean algebra. I introduced the tautology and the contradiction, the T and the C here, as the things that were identities for the operations. So this should be no surprise that if you and a statement with something that's always true, you just get that statement's truth values. And if you or with something that's always false, it's just the same as the original P. I also put them on the board, and I think these made sense to people. Usually these make perfect sense to people, that tautology is equal to or is equivalent to a sentence ORed with its own negation. One side or the other of this or sentence is true, and so the or is true. Similarly here, a statement anded with its negation, one side or the other of that is false, so you get a contradiction out of that. The double negation law doesn't really belong in either column. This is just something about not, so it has no reference to or and in it. But it's worth recording. If you take a double negative, you get back the original positive. Now that's not true in ordinary language. I think often it's true in English, but for instance in Russian, you put emphasis on a negation. In fact, you're required to do a double negative to talk about a negation sometimes. So yeah, double negation doesn't always mean yes. It doesn't always mean no negation at all, but in logic it does. If you not something that's been negated, you get back the original P. The next two rules are called idempotence. The etymology of idempotence is that it means the same as its power, or equal to your power. You see that P anded with P could be thought of as sort of the square of P. And so when you say P ands with P is the same thing as P, you're saying that P is equal to its own square, which is a power of itself. But honestly, that makes perfect sense. Try thinking about writing a truth table for P and P. It's going to have the same thing on both sides of it, so when P is true, it'll be true, and when P is false, it'll be false. And so it does the same values that P does. Similar remarks hold for P or P being the same as P. There are some other rules that involve tautology and contradiction. The first one, and I think we can skip the last one. Well, we'll see. I'll get there and we'll see it. These are called universal bounds laws. I want you to think about them a little bit like the way zero works when you multiply. You know what happens if you have 0 times any number? You get 0. It just doesn't matter. Multiplying by 0 gives you 0. So why is one of these universal balance laws like that? Here I have a contradiction anded with something, and I just get a contradiction. Here I have a tautology ored with something, and the result is just the tautology. So do you see how that's got a similar feel to the way 0 works under multiplication? 1 doesn't behave that way. So this is again a place where the Boolean logical symbols are more symmetrical than the ordinary logical things are. We saw De Morgan's law. We actually did a truth table for De Morgan's law, so that should be good. Just notice that it comes in 2 flavors. Here's the negation of an and being the or of a couple of negated things. Here it's the negation of an or becomes the and of things that have been negated. And lastly, well, next to lastly, we come to the weirdest law that's in the table. The ones that, if you capture their meaning and really understand them, become quite useful, I'll mention, but the absorption laws. And this is well, look at the left side of the one I'm circling here with my cursor. P ORed with P and Q. Seems like it might have some meaning, right? But the right side says, no, it just is the same as P. So why doesn't this depend on Q? Yeah, why doesn't it? Well, you can analyze it. What if Q was true? What will this be equal to? And what if Q is false? What will it be equal to? And you'll see that in truth, it does come out to be P. But that's tricky enough that I usually just ask people to fill out a truth table and verify that, wow, the result of P ORed with P and Q has no dependence whatsoever on Q, just depends exactly on what P does. It has the exact same values as P. And if you switch where's the and where's the or, P ANDed with P or Q, again, no, Q doesn't really enter into it. The There have been attempts made, I personally made these attempts when I was in high school, to try to prove this absorption law from the other stuff. It doesn't work. You just have to accept this as a independent thing. It is logically independent of the other statements, meaning you can't prove it from the first 9 things. Do I really need to say the 11 there? If you not negate something that's always true, you get something that's always false. And if you negate something that's always false, you get something that's always true. I think those make sense. So the weird ones here are De Morgan's law, which I believe we can work out with that. We can get used to that. You bring the knot onto the inside and you switch the direction of the connector. The absorption law, which you're just going to have to convince yourself is valid. And most of the rest of these things made sort of intuitive sense to us. So I hope that you won't feel too confused about them. Now, when we do our first quiz that involves logical equivalences, you'll get this sheet. You'll be allowed to look at this, but eventually I want you to be able to sort of know these things like the back of your hand. So practice the first quiz with the sheet, but later on we'll want to not need the crutch. All right. Okay, so that brings us to the end of the lectures for Thursday. What day is that going to be? The 3rd, I think, of September. So thanks for watching all this, and have a great rest of your day.